Dear student, in this video I'll explain how to draw the bending moment diagram for a cantilever beam loaded as shown in this figure. In this, the cantilever beam A, B, C, D is total of 1.5 meter length. It is subjected to a UDL of intensity 2 kilonewton per meter over a length of 1 plus 0.25 1.25 meter and a point load of 3 kilonewton at point B at a distance of 0.25 meter from the free end. As I have explained in the previous video, that is, shear force diagram for cantilever beam will follow the same procedure. Start from the free end and proceed accordingly. In this, the free end is towards right, so we will proceed towards left. And unlike shear force diagram, as I have explained in shear force diagram, if the UDL is subjected to a number of point loads in between, then we'll have to break the whole section into similar number of subparts. But in bending moment diagram, you need not worry for point load. Directly you can take a section starting from the free end till the completion of UDL, as we have done in the question related to bending moment diagram for simply supported beams. So we'll consider a section starting from the free end of the beam just before the completion of UDL, or the point where the UDL ends. You need not worry for the point loads. If there are any number of point loads in between, that will not matter. So now we'll write a generalized bending moment equation, that is bending moment equation at any distance x is equal to, now we'll follow the same sign convention, that is, if the load is downwards then that is negative, and if the load is upwards then positive. So starting from here, first for UDL. Now for UDL, the bending moment equation is plus minus WL square by 2, where W is the intensity of loading, L is the length over for which we are considering the bending moment, and 2 is a numerical value, and plus is for if the load is acting, intensity of loading is downward, and if the load is acting upwards, and if minus if the load is acting downwards. So in this present problem, the intensity of loading or UDL is acting downwards, so we'll consider minus. W is intensity of loading, that is W2. L is the section that is intercepted in between. So from here till here we are considering a section at a distance x. So the length of the cantilever in this portion is x, so 2x square. So WL square by 2, 2x square by 2. Now moving towards this, we have written the bending moment equation for the UDL for this whole section till x. Then we'll consider this point load. For point load, since the load is acting downward, so minus load into distance 3 into the distance of this load from the point where we are considering the bending moment. So this distance is how much? This distance is total length from here of this section is x, and this distance is 0.25. So this length is x minus 0.25. So x minus 0.25, and there is no other load in between. So finally we'll get the bending moment equation mx is equal to minus x square minus 3 into x minus 0.25. Now we'll find out the value of bending moment at the salient point starting from here at point A, that is x is equal to 0, because we are starting from here. This is the origin, and at this point the value of x is 0. Now ma is equal to minus 0 square. Now as I have already mentioned in the earlier videos, if we get a negative term inside the bracket, then we'll neglect it. Whether it is square or cube, that doesn't matter. We have to observe that if this portion within the bracket term is negative, that means we have to neglect it. The reason being, since we are calculating the bending moment at this point, so we have not arrived at this value, that is x minus 0.25. that is, we are not considering this section because this load is here, and we are calculating the bending moment A, and we are proceeding from this side. So that is why we are neglecting the negative terms. So for at point A, that is x is equal to 0, here this is 0, and this term will be neglected, so ma is equal to 0. As I have already mentioned earlier, that bending moment at the starting and end of the beam is 0, but in this case here it will not be 0 because there will be a reaction force, but here there is no any constraints, or so this is a free end, so bending moment at this point will be 0. Now at point B, that is x is equal to this distance 0.25. So putting the value of x here, so mb is equal to minus 0.25 square, and this term is 0.25 minus 0.25, that is 0. So this is equal to minus 0.25 square, that is minus 0.0625 kilonewton meter. This is the unit for bending moment. Now finally at point C, so bending moment at point C, that is x is equal to this whole distance, that is 1 plus 0.25, that is 1.25 meter. So mc is equal to minus 1.25 square minus 3 into 1.25 minus 0.25. So finally mc is equal to minus 4.563 minus 4.563 kilo Newton meter. Now we have to find out the bending. There is no load in between these two, so finally we have to find out the bending moment at point D. Now for this we cannot consider this equation, because if we are considering a section away from this, we have crossed the region of UDL, then this will be converted into a point load. So we cannot directly use this equation. We'll have to write a new equation. So first we'll convert this into point load. So A 3 kilonewton, 0.25 meter, and in order to convert this into point load, as I have explained in earlier videos, we'll have to find out the area of this rectangular portion, that is UDL. The height is same, so this is a rectangle, so area of this rectangle is height into length. Height is 2 meter, 2 kilonewton per meter, that is intensity of loading, and length is 1.25. So area is equal to 1.25 into 2, so that is equal to 2.5 kilonewton, and that will be acting at the midpoint of this rectangle, that at the center, that is midpoint, halfway from here or halfway from here. So that will be at a distance of 1.25 by 2. So a point load of 2.5 kilonewton at a distance of 1.25 by 2, and this distance is 0.25. So we have to find out the bending moment at point D. So directly there is no other, already we have calculated till point C, at point C. So finally we'll find out the bending moment at D. So we'll consider a single section at a distance x starting from the beam and just before D, and writing the bending moment equation, mx is equal to, this is downward, so minus 3 into this distance. This distance is how much? X minus this left distance, that is x minus 0.25, and for this minus, this is acting downward, so minus 2.5 into distance of this load from this section at a distance x, so that is x minus this left right distance, so x minus this distance, that is 1.25 by 2, and there is no other load. So we need not calculate, because we have already calculated the bending moment at this point. So finally we will calculate the bending moment at point D. Remember that if we are using a section x that is away from this UDL, that means if we have crossed the area of UDL, then we'll have to convert this into a point load, and then subsequently we have to use that point load in the bending moment equation that we have done here. So finally at point D, that is x is equal to this whole distance, that is this distance, that is 1.5 meters. So at x is equal to 1.5 meter, md is equal to minus 3 into 1.5 minus 0.25 minus 2.5 into 1.5 minus 1.25 by 2. So solving this equation, finally we'll get md is equal to minus 5.94. So now we'll draw the bending moment curve. So draw the cantilever beam, mark the salient points A, B, C and D. The value of bending moment at point A was 0. At B, minus 0.0625 kilonewton meter. At C, this is slightly higher, minus 4.563 kilonewton meter. And finally at point D, that we have calculated, 5.94 minus 5.94 kilonewton meter. Now while drawing the bending moment diagram, you will have to observe whether this is a point load or UDL. As you can observe, between A and C it is UDL. So for UDL you will have to draw a parabolic curve of this shape, as I have already mentioned earlier, and accordingly you have to select the portion that fits here. So between A and C you will get a parabolic curve. So you can consider a section, this one. So joining these points with a free curve, joining these points with a free curve, you will get a parabolic curve. And between C and D there is no load. So or whether if there is a point load, then you have to join that with point loads. So joining this with a straight line, because there is no load, or if there is a point load, then join with a straight line. And finally this is the bending moment diagram for this cantilever beam. So if you have to draw this parabolic curve between A and C, and if you want to draw a smooth curve, you can consider more number of points. That is, you can consider any number of points, say at a distance of 0.2 meter, 0.3 meter, 0.35 meter, from 0 to 1.25 meter, and accordingly putting the values in this equation, you will get a number of values of bending moment between A and C, and then by joining these different points you will get a smooth curve. So this is the bending moment diagram for this cantilever beam.